this started. All right, so we're going to look at parametric equations. So this was one of the first lessons that I did a couple of years ago when COVID hit. So if you go on the website, you'll actually see individual videos that I've made for each of these sections. So if for some reason you miss something, you don't feel like watching the whole hour-long video for class tonight, I think they're like 10, 15 minutes tops for each of the sections. So you can easily go through those and look at them, because I had to create them for my class when we went out on COVID at that point. So we're going to look at parametric equations, something that most people, if you've seen, it was briefly and probably for not very long. Most teachers don't really care for parametric and polar equations, and you typically don't end up seeing them until you get into calculus. Parametric equations allow us to graph non-functions. So if you look at that funky looking graph in figure 1, it is definitely not a function. It's going to fail the vertical line test instantly. So there's no way for me to write this as a function. However, if I write it as a function of a third variable, which we call our parameter, which typically is used as t, I can write it. So I'm going to look at my, instead of x equaling a number and y equaling a number, x and y are both going to be equations using that parameter t. And then we're going to be able to get that funky looking graph. It's known as a parametric curve. Desmos does allow you to graph these. It'll actually, you graph it using it as a point. And I'm going to show you a couple problems with using Desmos to graph these as well, so you can see how to do it and see what the graphs look like. But first thing I want to do is I want to show you actually how to get the graph by hand so you can understand what's going on. All right, let's look at example number 1. So we've got two equations here. We've got x equals t squared minus 2t and y equals t plus 1. When we're doing these, in essence, what we're doing is we're taking the values for t and plugging them into both equations and getting a point that we're going to graph. So the t is not graphed on my coordinate plane. The t is just telling me where that is. Basically, it's telling me the direction I'm going. So if we look at t equals -2, I'm going to plug in for the x. I'm going to plug -2 into that problem. So 2 squared minus 2 times -2. So -2 squared is 4 plus 4. So that comes out to be 8. And then I do the y, -2 plus 1. And I get -1. Likes the 1, but not the negative sign. Okay. Open this back up. All right, so this equals -1. Restarting my laptop. So we look at this point right here. We go over 8 on the x and down 1 on the -1. So that's the point that I'm going to graph. Underneath it, it says t equals -2 there. That basically is saying that when t is -2, that's the point. And when t is -1, I have 3, 0, 0, 1, -1, 2, 0, 3, 3, 8, and 8, 5. So it's like I'm basically going to plug these values in and get this table. The one other thing you want to notice on this is the arrows. the arrows are actually just as important when you're graphing this, because what you're looking at is the direction that the graph is going. Computer's got enough. So that's the direction we're going in. Does that make sense on where we're getting the X's and the Y's from?
I see where the X's and Y's are coming from, but how do you know the direction? Is it from least to most?
Yeah, basically it's the direction we're going in the T's. So typically you're going from T's from -2 to 4. It's the same concept of like we're going left to right on the X-axis. So you're never going to go the other direction. You're always going in the correct order of least to greatest. All right. Let's look at another one. My darn computer's restarting on me. So this time we have x equals cosine of t and y equals sine of t. So again, we're going to do the same thing, but this time when we're doing t, we're not going to use -1, -2, or -2, -1, 1, 0, those numbers. We're going to use radians. We're going to use pi. So we're going to go 0 to 2 pi for this one. So if t equals 0, what's x going to equal? What's cosine of 0?
One.
Yes. And then we do the y, that's sine of 0, which is 0. Then if I do t equals, let's do pi over 2. So cosine of 0 is going to be what? Or cosine of pi over 2 is going to be what? Think about your cosine curve. It's from 0, it's going to go down. So this would be 0. And sine of pi over 2 is 1. And we do t equals pi. So at pi, cosine is going to be -1. And y is going to be 0 again. 3 pi over 2.
Zero and -1.
Yep. 0 and y is going to be.
So we made a unit circle?
Yep, this is literally going to be the unit circle. So we've got x equals 1 and y equals 0, because we're right back to the beginning. So if we go over to Desmos, when we type this in, when you're doing parametric equations using Desmos, you actually put parentheses around it. So I'm going to do cosine of t, comma sine of t. And then you have to tell it where it's going from. So notice how it's stopping, because we didn't tell it where we're going from. So we're going from 0 to 2 pi. And we get a unit circle. So in essence, when you're writing it in Desmos, you're writing it as a point. You're telling me what the x is and the y is, but instead of using numbers, you use the equation. And then underneath it, you'll tell where t wants to go. So if I'm just looking at it from 0 to pi, I would just have half the circle. But in this case, I'm in the whole circle. So this actually is one of the ways that we can graph non-functions on a graphing calculator. So even like the Texas Instruments calculator and stuff has parametric equations ability in there that you can put your X and Y based on T, and it will graph these type of graphs on there. Got our graph. Oops. All right, let's look at the next one. See if this is going to work. So we've got our T, our X, and our Y. We're going to do the same thing again. So we'll use the same numbers, 0, pi over 2, pi, 3 pi over 2, and 2 pi. So now when we plug it in, what's sine of 2 times 0? So sine of 2, 0.
Zero.
Is still 0. And cosine of 2 times 0 would be
One.
still 1. The trick comes in when we're looking at sine of pi over 2. So now that's really sine of pi, right? Which is also 0. And it's going to end up being cosine of pi,
Negative
which
1.
is 1. No,
Negative 1.
negative 1. Cosine of, or sine of pi will be sine of 2 pi, which actually ends up being 0 again. And my cosine's back to 1. Three pi over 2 is 3 pi, which would be 0 and negative 1. And this one's going to be 0 and 1. So on the x's, they're all zeros. However, remember, we're not graphing, we're not coming up with every single point. We're coming up with the ones in between. So if we were to graph this one on Desmos, so we can actually see all the values. So 2t, 2t. We're still going from 0 to pi. Notice how it's the exact same graph. It's still the unit circle. But if you look over here, what did you notice happening with the cosine? It kind of repeated itself, right? This is actually going around the circle twice. And that's what that 2 did. So if I just did 0 to pi instead of 0 to 2 pi, notice I still have the exact same graph. So when we're looking at this parametric equations and we're going out, it can start looping and going over itself again and again and again. So if I took this one and went to 0 to 4 pi, it's just going around the same circle 4 times. Or 6 pi, it's going around the circle 6 pi, 6 times. So none of that's going to actually change the graph. And that's why knowing where it goes, like if I did pi over 2, notice how I only have half the graph now. So knowing where it goes and where it starts to repeat is also important when we're looking at parametric equations. Because when we're looking at functions, that never happened. All right, look at this one. Oh, here's another cool thing you can do with Desmos. Let's see if I can actually get this now. Change this to a table. You can actually add in tables and actually type the values in. There's a way to, I thought there was a way to actually change it to a table, but it's not letting me. All right, so let's look at this one. This one's sine of t and sine squared of t. So let's go to Desmos. We'll type it in and see what happens with this one. Turn this off. So I've got sine of t. And when you type in squared, you have to do it this way. Squared of t. So we've got that little bit going from 0 to that. So let's go to 0 to 2 pi and see what happens. All right, we've kind of got a parabola. So if I keep going up, I'm still going to get a parabola. So that's making a parabola that's just going to keep looping back and forth on top of itself. And we can start doing crazy things. Like this one makes a little loop. We can make things that we start playing with it. The trig functions kind of tend to do crazy things because the trig functions loop on each other. Like that's that function. And these are all just parametric equations. There's nothing like crazy about how we type them in and stuff like that. It's just a matter of how the actual points come out when you plug in those values in. And if we made this, if I did it from negative 2 pi, I get the opposite side. No, I have not figured out how to sign your name with this. Although there probably would be a way. This might be a lot more complicated of an equation. Any questions on what a parametric equation is before we start doing some math with it? That's the next step, obviously. All right. Math time. One of the parametric equations that you're going to see quite often is known as a cycloid. The cycloid is basically if you take a circle or a wheel or anything like that and you're putting a point on it and you're rolling it along the ground, it's what that point is going to create. So for example, if my point's right there, as it rotates, as it's rolling, it's going to start moving up, go to there, over, and then it's going to keep repeating itself over and over. That's known as a cycloid. It is one of the graphs that come up quite often because whenever you're looking at something rotating, it basically creates this shape. So it's something that's seen in engineering quite a bit. It's also used when we're looking at lenses. You can actually, the cycloid actually can create lenses as well. The equation for your cycloid is right down the bottom here, where r is your radius. So whatever radius you have on your circle, that's what we'll end up giving it to. So if we look at this on Desmos, we put this in there. So we can do, there's an actual really cool thing we can do with Desmos. We're actually going to put the r. So as my radius gets bigger, as my radius gets bigger, my cycle length gets bigger. As my radius gets smaller, and if it's negative, it actually flips over the other direction. So notice not only does it get higher, it actually gets longer because it's going to take longer for that point to go around the outside of the circle.
Would you go back to the page with the equation?
Yep.
Thank you.
So it's x equals r, and then I use t, they use theta, it doesn't matter, minus sine theta, and then the y is 1 minus cosine theta, not t minus cosine theta. High star. So that's the formula for a cycloid. All right, this is a calculus class, right? So now that we know what a parametric equation is, we're going to be able to do tangents to it and arc lengths and surface area and area under the curves, all that calculus stuff.
So is this our introduction to multivariable calculus?
Kind of. Multivariable calculus actually works when with x's and y's on the same side, because you're actually graphing it on a three-dimensional plane. So the equation's not actually solved for y or solved for x, it's actually solved for z. And then you're graphing it on the three-dimensional plane at that point. So, but yeah, this stuff kind of leads you into being able to not always looking at just one variable. So the formulas for it are slightly different though. All right, so the tangent, we'll start off with that. So basic differentiation. So as long as f and g are differentiable, we can do it, because not every function is differentiable. So the chain rule tells us that remember in chain rule, you find the derivative of the inside times the derivative will be on the outside. So the derivative of the inside would be the dx, and then the derivative of the whole thing would be the dy over dx, and that equals dy dt. We don't want it solved for the dy dt though. We want it solved for dy dx. So we just direct by. So the dy dx is the derivative of y, the derivative of the y function, and over the derivative of the x function. So you're just going to take the derivative of both pieces and divide them. And that'll give you your derivative for it. This over here, that's my second derivative. So we do the derivative of it again. But if you think about it, look at it, that right there. So it's the derivative of your new equation divided by whatever the derivative of the x was originally. So this is going to be your new derivative, and then we divide it by the dx dt again. All right, everybody got these equations down because we're going to use them. Okay, so here's what we're going to do. here's my parametric equation, and we're going to do some work with it. First thing I want to do though is whenever you're doing these, like I always have trouble visualizing, except for typical functions. Even when I was doing 3-dimensionals, I had trouble visualizing a 3-dimensional shape. Parametric equations are going to be that way for a lot of you. If you haven't seen them before and really haven't used them, it's going to be very hard for you to visualize what's happening. So what I would suggest, go to Desmos and graph it, just so you can start seeing what the graph looks like. So this way, when you're doing the work for it, the work will start to make sense when you start to see what the graph looks like. So we're going to graph this one. So we've got t squared. To the third minus 3. It goes 0 to there we go. -5 to 5. So here's what my graph ends up looking like. So that's my graph. So this way, when we're doing the actual calculations and start to look at things, we can understand where it's going at. So now, if we look at this, the first question says, show that C has 2 tangents at 0.30. So if we're looking at this, notice how my equation, when I was doing it, or the graph, it goes up that way. And then it turns and goes back that way. So at that point right there, there's 2 directions that hit that one point. So that's why there's going to be 2 tangents at that point. There's going to be one that's actually going down, and then there's going to be one that's going up, because there's actually 2 points at that one spot. Whenever we're looking for tangents, we're using a derivative. So we have our dy over dx equals dy dt over dx dt. So let's find dy dt. So that's the derivative of t to the third minus 3t. So that would be 3t squared minus 3. And then I have dx dt. That's the t squared, so that's just 2t. So my first derivative is 3t squared over 3 over 2t. Does the derivative make sense? All right, so the next thing I have to find out is I want to figure out what value of t gives me that point right there. So I need to know my t value for that point right there. So what piece of information do I know about that t point, or that point there?
X equals 0. Oh,
Not
sorry,
x
y
equals-
equals 0.
Right. So I've got x equals 3 and y equals 0. So you actually can do it with either one. It actually doesn't make a difference which equation you use. So I can use the X one or the Y one. Honestly, in this one, the X one's probably going to be easier to use. So for that point right there, I got 3 equals t squared. So if I do the square root of both sides, I got plus or minus the square root of 3 equals t. Okay. So I now know my t value that's going to give me that point. So I can now use that point, that value right here in this function here to find my slopes at that point. So let's do the first one. Slope at the square root of 3. So that's 3 square root of 3 times squared, 2 square root of 3. So I've got 9, that's 6 over 2 square root of 3, which equals just square root of 3. Actually, you know what I'm going to do? I'm going to do one extra step here because I have a feeling I don't remember how much you actually remember of rationalizing the denominators and stuff. So bring this up. So I've got 6 square root of 3 over 6, which is the square root of 3. Because when you bring it up, you basically multiply the top and the bottom by the square root of 3. And then let's find the slope at negative square root of 3. So I get 3 negative square root of 3 over 2 minus 3 over 2 negative square root of 3. So I've got 6 over negative 2 square root of 3, which this one ends up doing the same thing and gives me the negative square root of 3. We still actually haven't finished question A, by the way. We showed that it has 2 tangents. We did do that. We just now have to find the equations for those 2 tangents. All right. What's the equation for a linear? What's the equation for a linear equation?
Y equals mx plus b.
Yes. However, we're going to use, I'm going to use the point slope form of that because it makes our lives a little bit easier because we have a slope and we have a point. So I'm going to use this equation. So I've got my point is at 3, 0, and my slopes was at square root of 3 and negative square root of 3. So my equation is going to be y minus 0 equals square root of 3 x minus 3. So y square root of 3 x minus 3. And then the other one will be y equals negative square root of 3 x minus 3. All right. So now let's go and use this. I'm going to put those 2 equations on this graph so you can see. So y equals 3 x minus 3 negative 1. So see how those both go right down. So those are the two tangent lines for that graph there.
So the first part of the question said, show that it has two tangents, and the second part is find the equations.
Yep.
So which part would you consider us showing that it has two?
That's this part right here, where you're looking for the two t's.
Oh, but so because t equals plus or minus the square root of 3? Okay,
Since it has two values of t, it's going to have two tangents there. I just did the derivative first because I wanted to actually show you how to define the derivative. But yeah, that's technically finding it. Showing that it has the two tangents is that. And then we have to use the derivative to actually find the functions. And we're not done with this problem yet. So the second part of the equation says that it wants us to find any horizontal or vertical asymptotes. So we're still going to use the derivative. So that's my derivative. What do we know about a horizontal asymptote or slope? What slope's going to give me a horizontal line?
0.
Right. So if I'm looking for my derivative to equal 0, that really means I'm just looking at the top. Okay. So I just need to look at, make sure the top equals 0 and it doesn't make the bottom equal 0. So as long as the dy dt equals 0. And then my vertical asymptote will be the dx dt equals 0. So that'd be the bottom. So horizontal, I have 3t squared minus 3 equals 0. So 3t squared equals 3. So t squared equals 1. So t equals plus or minus 1. So I have two horizontal asymptotes. And then my vertical asymptote, I've got 2t equals 0, so t equals 0. So I've got one vertical asymptote.
Is it possible that there could be a non-existent? So I mean to say that there wouldn't be a horizontal or vertical asymptote?
Yes, that is possible.
Okay.
You do not always have to have a horizontal and vertical asymptote. All right, so the second thing, once you find that you have the horizontal and vertical asymptotes, we want to find those points. So when they gave us the points, so when they gave us their equations, we originally had x equals t squared and y equals t to the third minus 3t. So when we're looking for the points, we're going to go back to those equations to use them. So my horizontal asymptote, so let's do the first one. So t equals 1. So if I plug 1 into that, x equals 1 and y equals 1 minus 3, which is negative 2. So 1, -2. And then if I do t equals -1, I get x equals 1 and y equals 1. Well, that's -1 plus 3, which equals 2. So I got 1, 2. So those would be the two horizontal asymptotes. And then my vertical where t equals 0, x equals 0, and y equals 0. So that's 0, 0. While you're writing that down. If we look at those points, we have our 1, 2, 1, -2, and the 0, 0. If you look at it, it kind of makes sense that those are the horizontal asymptotes and then the vertical asymptote. All right. Next part. It wants us to find where the curve is concave upward and concave downward. So for concavity, we need to use the second derivative. So we're going to use that equation. So I know my x was t squared, my y was t to the third minus 3t, and my dy dx was 3t squared minus 3 over 2t. So let's find my second derivative. So the first thing I'm going to do, because in the first derivative I have a fraction, we'd have to use the quotient rule for it, but I could modify this equation a little bit to make my life a little easier. So that's what I'm going to do for this. So I'm going to split this up. So I'm going to take out the 3 over 2. I'm left with 1 minus 1 over t. So now I can just find the derivative of that instead of trying to find the derivative of using the quotient rule. So the derivative of that, the d dy.
Wasn't it 3t squared?
Oh, yeah. Yes. Hold on a second. Screw it. That's why. I'm looking at the answer and it's already had the derivative done. That's why. I'm like, wait a second, that doesn't make sense. So I have t minus 1 over t. That's better. Because the derivative of t is 1. All right, so I'm going to do the derivative of the dy dx. So the 3/2 is going to stay. Derivative of t is 1. And the derivative of 1/t is 1/t squared, because we're going to subtract 1 from it, make it squared, and pull out the -1. So that's why it becomes a positive. And now, so that's the top part. And we got to divide it by the original dx dt, which was just 2t. So I take that whole thing. So it's that divided by the dx dt. So that's divided by 2t. So again, more algebra. The 2 can come down the bottom. So I have 3, and we're going to make this the t squared plus 1/t squared over 4t. And then I have 3 t squared plus 1 over 4t to the third. So that's the second derivative. All right. So how do we determine concave up and concave down? So concave up is when my second derivative is positive, and concave down is when my second derivative is negative. So let's find it for 0, and we'll be able to figure out where it switches based on that. So we're going to take this problem and just set it equal to 0. So I've got 3 t squared plus 1 equals 0. So t squared plus 1 equals 0. Minus 1. T squared equals -1, which does not work. So that one doesn't work. Which other value is going to make this 0 or undefined? Wait, something? No. So I also have the bottom. Since the top doesn't actually give you a 0 ever, the bottom, I don't want to be 0, but I want to know where it switches from negative to positive, because obviously it can't be 0 down the bottom. So that actually is going to be, if I did that one, I get 4 to the third equals 0, so t equals 0. That doesn't obviously exist, but when t is negative, the bottom is going to be negative, and when t is positive, the bottom is going to be positive. So therefore, for concavity, when t is greater than 0, it's concave up. And when t is less than 0, it's concave down. Does that make sense? Does everybody understand why I couldn't use the top and why I'd have to use the bottom? That's the most important part here. All right. Next major part of calculus. Area. So when we're looking for area, we're looking at our integral. Now, in this case, I'm not doing the integral. I don't have just a y and a dx, but I kind of do. My y is g of t, or the function of y, and my dx is the derivative of whatever my x is in terms of t. So when I'm looking for the derivative or the integral, I'm going to take the y function and multiply it by the derivative of the x function. And that's how I'm going to figure out my integration. And we're always using the range that we're looking at. So whatever starting point and ending point, that's what we're looking for our area. So make sure in this situation that they don't repeat themselves. Otherwise, like the circle one, if we kept going around a circle, we're looking for the area of that. You only want to do one circle, not multiple circles, because you will get a bigger area than you'd expect.
What are those symbols on the second integral of that first equation?
The little a, the a and the b, it's
Are
just
those
it's lowercase alpha and lowercase beta.
okay?
It's just Greek letters for it because they didn't want to use the same a and b that they used for the y dx. But it doesn't make much of a difference in your actual writing. All right, let's use this on the cycloid. So we've got our x and our y. So remember, my integral is the y times the dx, basically. So I've got my y. I need to find my derivative of the x. In this situation, that r is a constant because they're basically saying whatever radius I have, I'm going to find the formula for it. So when I'm doing the derivative for this, we're treating the r as a constant. So dx is going to be r times 1 minus cosine theta. So theta becomes 1, and then the sine goes to cosine. All right, so we have, and we're doing this from 0 to 2 pi. And I have r times 1 minus cosine theta times r 1 minus cosine theta d theta. So I can take out the r squared. And I have 1 minus cosine theta squared d theta. So let's FOIL that out. And I have 1 minus 2 cosine theta plus cosine squared theta d theta. All right, so I can do the integral of the 1. I can do the integral of the 2 cosine theta. I cannot do the integral of cosine squared theta. So I've got to change that. So chances are you don't remember. If you do, we're going to use the half angle formula. So that right there is 1/2 1 plus cosine 2 theta. All right, so we can now do our integral for this. So the integral of 1, so I've got r squared, I got theta minus 2 sine theta, and then I got plus 1/2 theta plus 1/2 sine 2 theta. And evaluating from 0 to 2 pi. All right, so let's simplify this down a little bit. So I've got 3 over 2 theta minus 2 sine theta plus 1/4 sine 2 theta. And we're still doing it from 0 to 2 pi. All right, so if I plug in 2 pi to the first one, I've got 3 pi. Sine of 2 pi is 0, so that's gone. And sine of 4 pi is also 0, so that's gone. And if I plug in 0 to all these, they're all gone. So I get 3 pi radius squared. So that is the area under any cycloid. So why that's, so here's the nice thing. If you ever are working with cycloids, you don't actually need to go through and do all this workout. If you remember that 3 pi r squared is the area under the curve. That'll find your answer. And an easy way to remember it is it's 3 times the area of a circle. Because the area of a circle is pi r squared. All right. We got arc length left and surface area. Arc length. So when we were looking at a typical function, arc length would just be along the edge. Straightforward, quite simple. When we're looking at arc length on a parametric function, or a parametric curve, it can double back on itself. It can go backwards. So when we're looking at doing our arc length, you have to use the parts to find the pieces you want. So this is only going to end up going in one direction. So when we're looking at this, if we're going the other direction, you need to actually come up with going the other direction. So knowing where it switches is kind of important. The formula is basically the same formula we used for arc length before, except it's not 1 plus, it's the derivative of, or 2 times derivative, or 2 times derivative squared of the x and the derivative squared of the y. So that's the formula for arc length. Acts. So let's look at it. We'll do the unit circle. What's the circumference of the unit circle? What's the circumference of any circle?
2 pi r.
Right. So if it's a unit circle, it would be just 2 pi because the radius is 1. So let's do the arc length and see if I get it. So we're doing the from 0 to 2 pi, and we're using, it's the derivative of the dx dy, or not dx, dt squared plus dy dt squared. So 0 to 2 pi. So the derivative of cosine is sine. So that's sine squared of t. The derivative of sine is cosine. So that's cosine squared t. Notice I just completely ignored the signs because I was squaring it, so the signs did not matter. Sine squared t plus cosine squared t is 1. So that's the square root of 1. So it's just 1. So the integral of that is going to be t, going from 0 to 2 pi. So that would be 2 pi. Totally makes sense. Totally works. Now let's do this one. So the only difference in this one is the 2t inside. So the dx dt, remember we have to do the chain rule. So it's 2 cosine 2t. And the dy dt is 2 sine 2t. Oh, sorry, negative. I have to care about my signs here. I haven't squared it yet. So 0, 0 to 3 pi. So I have the square root of that. So it's 4 cosine 2t plus 4 sine 2t squared 2t. So 0 to 2 pi. I can pull out a 4 out of this, and the cosines still go to 1. So that's the square root of 4. So I'm doing the integral from 0 to 2 pi of 2. So it's 2 from 0 to 2 pi, which is 4 pi. Now, if you remember those two equations from the beginning of this, when I first showed them to you, you'll remember that they both give you a circle. The difference is this one goes twice. So that's why I was saying you really have to pay attention to where it starts to repeat itself. So this one, I wouldn't have wanted to go from 0 to 2 pi. I would have just wanted to go from 0 to pi because it repeats itself.
So how will we know that in a problem?
Graphing it and looking at it.
So we should start by graphing it.
Yeah, that's why I said when you're doing these, I would always graph it so you can have a general idea of what the equation looks like. Because even if you remember it when we did this one, by graphing it, you started to see it. It's like, okay, it's crossing twice there. It's like that's why we're going to have 2. It's like that looks like a horizontal asymptote up there. That one looks like one down there. So it's like you can start to see that information. Where if I just took this and started doing it, and you didn't even look at the graph, it'd have been extremely difficult for you to visualize where those things actually were. So that's why I always start off with graphing. All right. No, I'm not gonna do that one. Let's just go to the surface area. All right. Surface area. If you remember, when we were doing surface area, it was basically the arc length rotated. So depending on where it's rotating depends on the direction you're going to do. But the only thing that actually changes is the thing in the front. It's either going to be the Y or the X, depending on which side you're rotating around. So, but it's 2 pi Y or 2 pi X times the arc length, which is that. So really the only thing different between this and what we did when we did the surface area originally is it's not 1 plus, it's the dx dt plus the dy dt.
So what's the second equation there for?
It's the ds. So if you look at here, see how they have the 2 pi y ds and 2 pi x ds. It was just another way to see it when we were looking at it in, was it chapter 6? They wrote it slightly different. Actually, no, it was chapter 8 when we were doing the arc length stuff. They pulled out that second part and just wrote it as ds. So this way you could look at, since you knew the arc length was already there, that was the arc length piece.
All right, thanks.
All right, last one. Let's find the surface area of a sphere. Well, let's prove the surface area of a sphere is 4 pi r squared. So if I'm going to look at the surface area of a sphere, that means I need to take a half circle or a semicircle and spin it. So if we remember from what we just did, my circle is this. So that's going to always give me my circle of whatever radius I want. The unit circle is just a 1. If I just want the half circle, the semicircle, I'm not going to go from 0 to 2 pi. I'm just going to go from 0 to pi. Because I only want the top half. If I took the whole circle and spun it, I would end up doubling the information because it's going to go on top of each other. So that's why I'm just looking from 0 to pi. Since this one, if we graph it, so this is where graphing and seeing that. Where did my Desmos go? Lost my Desmos. So we know which direction we're going. Actually, I'm just going to use those simple. So in this one, we're rotating it around the x-axis. So my radius, which is what we're looking for to be the piece in the front, is going to be my y. So I have from 0 to pi of 2 pi times the y, which is r sine t. And then my derivative of both pieces. So I have negative r sine t squared plus r cosine t squared. So I can pull out the 2 pi, so I don't have to worry about that part. I have r sine t. I have r squared sine squared t plus cosine squared t. So 2 pi, that's going to be r, so I have r squared sine t, and that part is 1, so it's down to that. I can pull out the r squared, so we're just doing the integral of sine of t. Which is negative cosine of t, and we're going from 0 to pi. So I've got 2 pi r squared. When I plug in pi to that, I get negative 1, so that's a 1. And when I plug in 0 to that, I get a 1. So I have 4 pi r squared, which is what we were trying to prove. So when your geometry teacher told you that the formula for surface area of a sphere was 4 pi r squared, and you said, how do we know? Can you prove it? I guarantee your math teacher didn't go, sure, let me do integration to show you it. They probably said, it's the formula, just memorize it. Because this is how you'd actually have to prove it. All right. And that's parametric functions, or parametric curves. On Tuesday, we look at polar.
Is it polar inequalities or polar equations?
Polar equations. And polar just deals with, so if you ever looked at a polar graph, I'll show you. So polar graphs are not rectangular. Polar graphs are circular because you have your radius and your angle that you're turned at. So that's your two pieces that you're looking at when you're dealing with polar. So that's what we're going to look at on Tuesday. So it'll be the radius r and then the theta will be the two things that we're concerned with.
So throughout this class, you have always told us that, you know, like we had earlier the square root of a negative number, and we said that that didn't work. Do
Correct.
imaginary numbers ever come back into calculus?
I'm trying to think. So the values still, they don't exist because they're imaginary. And most of the stuff you're dealing with calculus, you're actually trying to find a very specific real thing like arc length or area and stuff like that. So for the most part, no. Now, when you get up into the higher levels of math, yes, they do come back. So imaginary numbers and complex numbers don't go totally away. But when we're looking at like tangent lines and slopes, they can't be imaginary. When we're looking at area, it can't be imaginary. It's got to be a real value. So for this stuff, the basic stuff, when we're looking at that parts of calculus, no, it doesn't. When you start looking at the higher levels of math and the higher levels, when you start getting further along and using differentials and those type of things, differential equations and stuff, they can come back into play.
All right, thank you.
No problem.